This is section 14.1 on iterated integrals, and this is part 2. Example 5 is to evaluate this iterated integral. And so we have an outside integral with respect to x. We'll leave that alone for the time being. The integral from x equals 0 to x equals pi over 3, and then be a dx. And we'll evaluate the inside integral with respect to y. From 0 to 7, y times the cosine of x dy. But remember, since we're integrating with respect to y, the cosine of x is a constant. And so that would be like integrating y times 5, which would be 1/2 y squared times 5. So what we're going to get in there will be 1/2 y squared times the, quote, constant cosine of x. That's the integral, evaluated from y equals 0 to y equals 7. So let's do that, plugging in now of 7 and then 0 for y and subtracting. So we'll get the integral as x goes from 0 to pi over 3 of 1/2 times 7 squared times the cosine of x minus 1/2 times 0 squared times the cosine of x dx. So we've plugged in 7 and 0 for y and subtracted. Now let's clean it up a little bit and then we'll do the x integral. Okay, so we got the integral from x equals 0 to x equals pi over 3 of 49 over 2 times the cosine of x minus 1/2 times 0 squared times the cosine of x. That whole thing is 0. So that's it. Now we can bring the 49 over 2 outside of everything, times the integral from 0 to pi over 3 of the cosine of x dx, which would be 49 over 2 times the integral of cosine is sine of x, which you need to evaluate from 0 to pi over 3. And I had mentioned before how with these double integrals they usually make a point out of writing the variables, what they are. But it's not entirely necessary, and I didn't do it on the inside one up here, for example, y equals 7, y equals 0. It's not wrong to leave those variables off. It can help to keep things organized for your own purposes as you go through a problem. Usually once you get down to this stage, after you've integrated the y out, it's a single variable problem like Calc 1, and it's probably not necessary at that stage to write the x equals. But you can, for sure. So 49 over 2 times the sine of pi over 3 minus the sine of 0. So the sine of pi over 3 is radical 3 over 2. So we'll get 49 halves times radical 3 over 2 minus the sine of 0, which is 0. So we'll get 49 radical 3 over 4. Areas can be represented as iterated integrals, okay? And it can be set up in 2 different ways. An iterated integral can be set up in 2 different ways to calculate an area. One is this: a equals the integral from x equal a to x equal b. And what the x values are there are the left and the right boundaries of the region. Here's our region in this problem. This goes from x equal 1 to x equal 2. Of the integral from y equals g1 of x to y equals g2 of x. Those are the lower and the upper boundaries of the region, respectively. So this region is bounded below by y equals 1 and above by the function x squared. And then the integrand here, it looks a little, missing. Something's missing here. It looks a little incomplete, but the integrand is 1. So the integral from x equal a to x equal b, the left and the right-hand boundaries of the integral from y equals g1 of x, the lower boundary, to y equals g2 of x, the upper, of 1 dy dx, is the formula for area. So in this particular problem, that area integral is set up this way. And before we start calculating these areas, I'm going through a couple of examples of how they would be set up. And just another one. And let's set it up the other way. There are two ways to set this up. The other way to set up an integral for the area is to interchange the order of integration. What that means is, here's the second formula, the integral from y equals c to y equals d of the integral from x equals h1 of y to h2 of y dx dy. And what interchange the order of integration means is, if we compare this to the other formula which is up above, you can see the first formula was dy dx, and the outer limits were x equals and x equals, corresponding to dx at the end, so to speak. Now we've switched the role of dx and dy, so we have y equals c to y equals d, and dy will be the second variable with which we integrate with respect to. So what's what in this second version of the formula? Okay, because it's similar to before, but everything is interchanged. So y equals c and y equals d are the lower and upper boundaries of the region. So in this particular problem, y equals 1 is the lower boundary of this region. And y equals, now this isn't a nice integer on the grid. We have to figure that out by getting the point of intersection of these two curves, which turns out to be 5/3, 25 over 9. So this y value is 25 over 9. So the c value in this problem would be 1, and the d value would be 25 over 9. Now, what h1 of y represents is the left-hand boundary of the region. So in this problem, that's this parabola here. But we need to express it as x equals h1 of y. So that's a little switcheroo from the usual y equals a function of x. And that's what this here is all about. The point on that parabola, expressed as x comma f of x, is x comma x squared. Y is x squared. We need to solve this equation for x, take the square root of both sides, to express that point, same point, as square root of y comma y. The h2 of y function represents the right-hand boundary, x equals h2 of y. So in this problem, that's this parabola here. So we need to do the same kind of thing. We have that parabola is y equals x squared minus 6x plus 10. We have to solve that equation for x. Which gives us x equals square root of the quantity y minus 1 plus 3, comma y, is a different way to express this point. This way is in terms of y, which is what we want. And so those expressions for x in terms of y are the functions x equals h1 of y and x equals h2 of y, which are the left and the right-hand boundaries of the region. So this would be a way to set up an integral for the area of that particular region. So here's an example of setting up and evaluating an iterated integral for the area of a region. Here we have bounded by x equals 0, which is the y-axis, y equals 0, which is the x-axis, and y equals 16 minus x squared, which is that parabola. So we're looking at the area in here. And to set this up as an iterated integral, this is one formula for area that we can use. The integral from x equals a to x equals b of the integral from y equals g1 of x to y equals g2 of x of 1 dy dx. And we need to answer the questions. What are a, b, g1 of x, and g2 of x? Now, in general, what they are is a is the left boundary of the region, and b is the right boundary. And so in this problem, a and b we're going from 0 to 4. X equals 0 to x equals 4. G1 and G2 are the lower boundary and the upper boundary of the region. And in this case, we're going from y equals 0 to y equals 16 minus x squared. 16 minus x squared is the upper boundary of this region. Now we can work this out. This is equal to the integral from x equals 0 to x equals 4 of, we'll do the inside integral, which is the integral of 1 with respect to y. So that's y evaluated from y equals 0 to y equals 16 minus x squared dx. And this will be equal to the integral from x equals 0 to x equals 4 of, plug in now, y is 16 minus x squared, plug into the y, so that will be 16 minus x squared minus, plug in 0, y equals 0. So that will be minus 0 dx. And so we get the integral from 0 to 4 of 16 minus x squared dx. And that will be 16x minus 1/3 x cubed evaluated from 0 to 4. And that turns out to be 128 thirds. Now I want to set up that one the other way as well, which would be y is now the outer integral compared to x was before. So the y limits of the region are going to go from 0 to 16. That's here to here. The left-hand boundary of the region is x equals 0. Here to point here. Now this is what we have to figure out a bit, because we know this point as x comma y, which is x comma 16 minus x squared. But what we need to do is express it, I'll leave some room there, as a function of y comma y in order to set up this integral. So what we need to do is solve this equation for x. And that's down here, y equals 16 minus x squared, solve for x. So I switch the x squared over to the other side and the y over to the other side, which gives us x squared equals 16 minus y, and then the square root of 16 minus y. So a point on this parabola can be expressed as the square root of 16 minus y comma y. And since we need the x value for the right hand boundary of our region, that's going to be the x coordinate of that point, the square root of 16 minus y. That's what goes right here.